Alright, so now we're going to do problem 59 from chapter 9. In this diagram, we see that block 1 has mass, that's 2 kilograms, that's moving rightward at 10 meters per second. So that's called a V1, that's 10 meters per second. And block 2 that has a mass that is 5 kilograms. And it's moving rightward at 3 meters per second, so that's your V2. And the surface is frictionless, so you don't have to consider friction. And the spring, with the spring constant, 1,120 Newton per meters, is fixed to block 2. So K is 1120 Newton per meters. Is fixed to block 2. When the blocks collide, the compression of the spring is maximum at the instant the blocks have the same velocity. Find the maximum compression. All right. So what does that mean? It means that you have, you have both blocks. They are moving rightward in the same direction, and when they're going to, collide with each other. Once they collide with each other, then they're going to move forward together as well. So you can see that this is it looks like inelastic collision. However, because you have the spring that acting as a buffer, so it is an elastic collision. What does that mean when it is an elastic collision? It means that linear momentum has to be conserved, and also energy has to be conserved as well. Okay. So this problem is different from the previous one that we did. Previous one was inelastic, but this one, because there is a spring acting as a buffer, so there's no energy loss during this elastic collision. So in this case, you can use both the conservation energy and also conservation linear momentum. So they move together. They move together with the velocity, and it's found that when they move, you want to find at what velocity when the compression is at maximum. Okay. So, first of all, we need to find out what is the velocity. In other words, this one is moving at the velocity. This one is moving velocity. After collision, they're both moving at the same velocity. So we can use initial linear momentum that's equal to the final linear momentum to figure out what this velocity is. When they move together. So you have your M1, V1, and you can see that I dropped the vector sign because this is the horizontal motion. So you have M1, V1 plus N2, V2. That's before collision. After collision, you have the combined mass, M1 plus M2, and then times the velocity, which is unknown. So you can just plug in the numbers, 2 times 10, and then plus 5 times 3, and that gives you 2 plus 5, and then times v. So how fast is the system moving? It will move at 5 meters per second. Okay. So this is after collision. We found that they will move together at 5 meters per second. And then the second part asks you that at what the second part asks you when they collide, the compression is at maximum at the instant, and the block have the same velocity. You want to find what is that compression. Okay, so we can see that because this is the before collision and after collision, energy is conserved because this is an elastic collision. So if this is elastic collision, it means that P is conserved and kinetic energy is conserved. Okay. So then, so how do we figure out what is the maximum compression of the spring? So let's go back to these pictures again. This one is moving. This one is also moving. So they both have the kinetic energy. So we know the initial energy during this system is the kinetic energy of this one plus the kinetic energy of that one. Okay. And after collision, while the spring, is compressed to the maximum, it is moving at this velocity. So we know that there are two kinds of energy are present. One is kinetic energy, and the other one is the spring potential energy. Okay, so that's so based on that, we can set up equation saying the initial energy is equal to the final energy, and initial energy only the initial energy is only in the form of kinetic energy. So you have 1/2 m1 v1 squared plus 1/2 N2 V2 squared. This is your initial energy. Okay, so you can plug in the number quickly because N1, N2, V1, V2, they're all given. That has to be equal to the final energy. After collision, we can see that both the two block system moving at the same velocity, so it has kinetic energy. Simultaneously, this spring is being compressed at the maximum. So it has spring potential energy. So you have 1/2 combined mass, and then times V squared, and then plus 1/2 spring constant, and then times the maximum displacement, or the maximum compression. So this set up the equations and based on the conservation energy. So you can just plug in the numbers. So you have 1/2 times 2 times 10 squared, and then plus 1/2 times 5 times V2 is 3. This is on the left-hand side. On the right-hand side, you have 1/2 2 plus 5. And then times V. V we calculate to be 5 squared. And then plus 1/2, your K value is 120, and then times your D squared. Okay? So once you plug in the numbers, your D value, after you plug in the numbers, let's see, your D value, you should get 0.25 meters. Okay, so this is the maximum compression of the spring after collision, and that because the spring is being compressed, which means that there, it stores spring potential energy. Okay, so that's problem 59. And the next one, we're going to do problem 95. All right, let's see. Let me just draw a diagram first. Okay, so let's see, problem 95. In this arrangement, billboard 1, moving at a speed of 2.2 meters per second, undergoes a glancing collision with the identical billboard 2 that is at rest. So this is ball 1, this is ball 2, and it's moving this rightward direction, and it's going to glance and collide with the ball 2, and ball 2's initial velocity is 0. Now, after collision, ball 2 moves at a speed that's 1.1 meter per second at an angle that's 60 degrees. And so you'll also find the main to end directions of velocity of ball 1 after collision. Now, do the given data suggest the collision is elastic or inelastic? So several things here. You have one, so you have like two ball system. So you have that each is going to have its own velocity. So I would suggest that you would say that instead of VI, you would say that V1, ball 1, initial velocity, that's 2.2 meters per second. And this is ball 2. So ball 2 has initial velocity. So it's 2 V2I, that's 0 because it is at rest. Now so this is before collision. After collision, ball 2 is moving in this direction, so this is your V2F, and then this is the this is the first ball that is moving in this direction, so we call that V1F. Okay, so you can see that we have 4 different velocity before and after. We know 3 of them, but we don't know how fast is the ball 1 is moving after collision. So your task is to find out what is the magnitude and also what is the angle. The other thing is that you'll also find, after you do the calculation, you'll also find to identify whether this is elastic or inelastic collision. Okay, so while the problem didn't say that it is elastic or inelastic, which means that you cannot use the conservation of energy to do this problem, what you have to use is instead the conservation of linear momentum, because it's always true when you have an isolated system. So let's say this is a two-dimensional, this is two-dimensional. What does that mean? When it's two-dimensional, it means that the conservation in momentum has two equations. One that has to be satisfied in the horizontal direction, and the other one that has to be satisfied in the vertical direction. So in other words, you would say that initial linear momentum, the vector linear momentum, that has to be equal to this, and they are in vector form. So this basically consists of two equations. One is that the horizontal component before and after collision, and also the has to be equal to each other, and also the final linear momentum before and after the collision, and that should be y. I'm sorry. Initial in the y direction has to be equal to the final in the y direction. Okay, so these are the two. So you should have two equations. Now, based on this, we know that this one is moving in this direction. So it has a linear momentum, that's velocity times the mass of this one. And because mass is not given, so that just assume that both balls, they are identical. So that just assume that they have the same mass m. Okay, so we have initial. Let's see what is the linear momentum in the horizontal direction. Initially, you have your m. That's your m1, and then v1I, because it's moving only horizontally, okay? This turn has no velocity, so you don't have to include that, so just plot 0. This is before collision. After collision, then this one is moving at this velocity, and it has a horizontal component, and that horizontal component is just basically, and in terms of the, so this is your, so we have mass of ball 1, and then times v2f, the final velocity, but then you have to use the horizontal component. So the horizontal component will be this, right? So that will be cosine 60 degrees, okay? So this is the horizontal component of ball 1, ball 2. What about ball 1? For ball 1, you have mass of the ball 1, final velocity of the ball 1, and then this is theta. So let's say the horizontal component, again, is in this direction. So that's your cosine theta. So you have cosine theta. So let's look at what we have here. You have your m, so they all have n, so they cancel. So you can see that the mass really doesn't matter. Now, v1I is 2.2. That's equal to v1f, that's 1.1 times cosine 60, and then plus v1f cosine theta. Now, we can see that your v1f is unknown. Your cosine theta is also unknown. So we just leave it at that for the moment. So this is the equation from the conservation of linear momentum in the horizontal direction. Now let's move on to additional information. That is when the linear momentum is conserved in the vertical direction. So vertically, before collision, this ball 1 does not have any vertical velocity, and ball 2 is not moving. So before the collision, there is no initial linear momentum in the vertical direction. Okay, because this one is primarily moving in the horizontal. So vertically, nothing. This one is not moving at all. So no contribution. So on the left-hand side of the equation, there is zero linear momentum. If the before collision, the linear momentum in the vertical direction is 0, then after collision, the sum of all the turn has to be equal to 0 as well. Okay, because momentum is conserved. So let's see, you have V2, so MV, so the contribution from ball 2, that will be, it has a velocity component in the vertical, that is sine of 60. So you have V2F and then sine 60. Okay, so that's positive because it's pointing upward. Now let's look at V1F. V1F will also have the y component, but it's negative. So, and we use a small angle, so theta, we take it to be positive. So you have minus. You have to manually put a minus sign because these two, they should cancel each other. Okay, so you have minus, and then I should also, to be rigorous, let's put the mass in. So you have mass, and then times the vertical component of the velocity, and so that's from ball 2, and then mass times v1f, and then times sine theta. Okay, so you can see that again, mass get cancelled. So what we have here is that you have V1F. So I'm going to rearrange that. V1F sine theta is equal to V2F sine 60. So you can see that on the right hand side, these are all known values. So you can calculate the value. But then you still have like 2 unknown. But at least we have like 2 equations, 2 unknowns, so you can solve for the unknown. Okay, so let's see how do we do that. So let's see. So in other words, V1F sine theta, after you plug in the number, so this is 1.1 sine 60. So after you plug in the number, you should have 0.95. Okay, so this is 0.95. And then V cosine theta. So let's go back to this equation. So V cosine theta, this is V cosine theta. So V1F cosine theta is equal to 2.2 minus 1.1 cosine 60. So you should have a value that is equal to, let's see, do I have that value? Let's see. Okay, that just leave it. So you'll have some value there. Okay. So in other words, so what we have here is that you have V1F cosine theta that has this value, and then you have V1F sine theta that has this value. So what you can do is that you can just do substitution, whichever you do, or you just divide both sides. So you have so V1F get cancelled. You got the inverse. You got the like 1 over tangent, and then you have some numerical value. And after you do that, so let me after you do all this, then tangent theta. Let's say the tangent theta. What you have here is that you have. Let me just erase this. You have 0.95 over 1.65. So that gives you theta that's equal to 29.93 degrees. Okay? So once you have your theta, you can just plug into this equation or that equation, and then that will give you V1F. So your V1F, after you plug in the numbers, so because V1F sine and then theta is 29.93, and that's equal to 0.95. So you can calculate your V1F. And so your V1F, after you do calculation, you got 1.9 meter per second. Okay? So you can see that we figured out the theta. We also figured out the magnitude of the velocity based on conservation of energy and based on conservation of linear momentum. That is in the horizontal direction and also in the vertical direction. Okay, so let's see. So after you do all this calculation, you'll also ask to find whether this collision is elastic or inelastic. So what you have to do is that whether the initial kinetic energy is equal to the final kinetic energy. If they are equal to each other, then we say that they are they are elastic collision. If they are not even close to each other, then we say that it is inelastic collision. So you can quickly calculate your initial kinetic energy. That will be just 1/2 m, and then V1I squared, and then plus 1/2 m V2I squared. Now, because V2I is 0, so that does not contribute. So you can quickly calculate. So you have 1/2 m, and your VI is 2.2 squared. So that's your KI. It is okay. We don't know the value of the mass because both cells will have a mass. So you can just compare this numerical value in terms of mass. Okay. Final kinetic energy. That's 1/2 mv V1F V1F squared, and then plus 1/2 n V2F squared. Okay. So whenever you calculate kinetic energy, it is always the total velocity that go into the calculation. You don't resolve it into x and y because kinetic energy is a scalar. If it's scalar, you use the total velocity. Okay. So what we have here is that you have 1/2 mass, and then V1F. Your V1F we calculate to be 1.9 squared, and then plus 1/2 n V2F is 1.1 squared. And you can see that when you add this. When you add this together, that will be around, you can combine this. So it's actually 1/2 n, and then 1.9 plus 1.1, that gives you 2. 1.9, and that gives you, what does that give you? So that's 2.2 squared. So you have 1/2 n, so 1.9. Anyway, so after you do the calculation, you'll find that they are equal to each other. So my ki after do that, this is like this is equal to 2.42 times the mass of the ball, and then after you punch into a calculator, this gives you around 2.42 mass as well. So you can see they are identical to each other. So it means that this collision is is elastic. Okay, so it's basically to find out whether they are elastic or inelastic, you just have to calculate the kinetic energy and see if they are equal to each other before and after the collision. Okay, so that's 95. And the last one we want to do is problem 100. So, and I'm going to leave this here. So this problem, again, is two-dimensional and involves collisions of two balls. So is it 100? Yes. Let me draw the diagram here. So you have a rightward moving M1, you have M2, and after collision, M1, so this is M2. After collision, M1 goes in here, okay, and make an angle that's 22 degrees. And M2 is actually moving in this direction and make an angle theta. So this is your M2. Okay, so this diagram includes the before and after the collision. Okay, so let's look at the problem. So in a gain pole, the cue ball strikes another ball of the same mass and initially at rest. After collision, the cue ball moves at 3.5 meters per second along a line making an angle 22 degrees with the cue ball's original directions of motion. So the velocity here, we call that V1I, that's 3.5. I'm sorry, V1F after collision. Okay, it moves at 3.5. And the second ball has a speed of 2 meters per second. So V2F. So V2F is 2, and you want to find the angle between the directions of the motion of the second ball and the original directions of the motion of the cue ball, and the original speed of the cue ball, and is the kinetic energy conserved. So in other words, this problem, you have this one with the initial unknown velocity, so that's called a V1I, we don't know, but it's moving in this direction, and collide with this ball, which has initial velocity that's, again, 0. So that's V2I, that's 0. Okay. After collision, this the ball 1 moving in this direction, making the angle 22 degrees with the velocity that's 3.5, and this ball is moving in this direction and making an unknown angle, but we know the magnitude, which is 2. So we also find what is initial velocity. So again, this is a typical typical collision problem. We don't know, again, whether it's elastic or inelastic, so you can't use the conservation of energy to solve this problem. What you can do, what you can use is that you can use this conservation linear momentum. And again, this is two-dimensional, so which means that linear momentum in the horizontal direction and the linear momentum in the vertical direction, they all have to be conserved. Okay, so we can set up the equation like this. Initially, This one is moving. This one is not. So we know that this has no contribution whatsoever to the linear momentum in the horizontal direction. And this one has a rightward linear momentum. So that's our initial linear momentum. So we have M1 and then V1I. So the set of equations like that, that's before collision. And then after collision, we can see that this one, M1 is moving in that direction. So you have your M1 and then the component, the horizontal component, the velocity is moving in that direction, but the velocity in the horizontal component will be the cosine of this velocity. So you have your M1 and then you have your V1F and then times cosine 22, okay? And likewise, this one, M2, is moving in that direction, so it has also a rightward direction contribution to the linear momentum, after collision. So that is, so you use plus, and you have your M2, and you have V2F, and then times cosine, and then theta, which we don't know. Okay. So in other words, is the mass given. Okay, M1 and M2 are equal to each other, so we can just drop the mass, so we just call that M. So, and you can see that every term has an M, so you just get cancelled. So your V1F, V1I is equal to V1F, which is 3.5 cosine 22, and then plus V2F. V2F is 2, and then times cosine theta. So we can see that, again, this equation has true or no. You can't just use this equation to solve for one of them. What you need to do is use additional information that will be coming from the conservation of linear momentum in the vertical direction. So before collision, there's no contribution from ball 1, there's no contribution from ball 2 because one is not moving, one is moving only in the horizontal direction. So on the left-hand side, you would say it's 0. And on the left-hand side. On the right-hand side, we know that this one has a vertical component. This one has a vertical component from the velocity. So the linear momentum will just be mass times. So it'll be mass. That's your M1. So let me just label that M1 and then V1F, and then times sine 22. That's upward. And this one produces a downward velocity, so that and so it's minus M2, V2F, and then sine theta. They have to be balanced each other because there's no initial linear momentum in the vertical, so that so whatever you have here, they have to cancel each other. So M again can get canceled. So what we have here is that you have V1F. V1F is 3.5. And then sine of 22 minus V2F, with V2F is 2, and then sine theta. Okay, so you can see that from this equation, you can quickly calculate your theta. So let me see if I have my theta. So my theta, after you use this, so what you have here is that you have your sine theta is equal to 3.5 sine 22 over 2. So your theta is equal to 41 degrees. Okay. So once you have your theta, which is 41 degrees, then you can plug into this equation and then calculate your V1I. So your V1I, after you do the calculation, your V1I, you should get, let's see, 4.75 meter per second. Okay, so that's your V1I after you plug in the numbers. Okay, so your theta here is 41. That's positive because we already, use a small angle. So that's, but we know that it is below the horizontal axis. So it's just 41 degrees below the horizontal axis. And V1I is 4.75. So again, you're asked to find whether it is elastic or inelastic. In order to answer that question, you'll have to say whether this and this are equal to each other. So we can just quickly do the calculation. So you have your Ki, which is 1/2 M1 V1I squared. V2I has no contribution, and then so we'll just leave it at that. So you have your 1/2 mass, and then V1I is 4.75. So you square it. Let me see if I did a calculation. So you got 11.28 M. Okay, times the mass of the ball. Now, the final kinetic energy is 1/2 M1 V1F squared, and then plus 1/2 M2 V2F squared. So we can just, so you have 1/2 M, and then V1F your V1F is 3.5 square root, and then plus 1/2 n, and your V2F is 2, so you square it. After you do the calculation, that gives you 8.125 times the mass of the ball. And you can see that initially you have this amount of energy, and after collision, you only have this amount of energy, which means that the energy, they are not equal to each other. And so you can say that this is an inelastic collision because they are not equal to inelastic, because they are not equal to each other. Okay? Because they are not equal. All right, so that's basically it.